Hello calculus fans, and welcome to section 7.3 where we talk about integration by trigonometric substitution. So in 7.1 we learned about integration by parts. In 7.2 we were integrating with sines and cosines and secants and tangents. And in 7.3 we continue with our integration techniques, and this time we're going to be working with integrals that have this sort of a form to it. It doesn't have to be a square root, as we'll see, but it'll have this a squared plus x squared, a squared minus x squared, and x squared minus a squared look to it. Okay, so in this section we're going to discuss a method for evaluating integrals containing radicals by making a substitution involving trigonometric functions. Okay, and we're going to be working with integrals that contain expressions that look like these. Now, a is the constant, so you've got a constant squared plus a variable squared here, and then of course the subtraction here, and then here the constant is first the variable's first minus the constant squared. So a is a positive constant, and the note is that these could also be something like a squared plus x squared to the 3/2, and etc. Things like that. So it doesn't have to be the square root. It could be other powers. So to get started, let's say we have an integral like this. We've got this one here. And with this one we think, well, how about, looks like maybe u substitution work, because if I let u be x squared plus 4, and I take the derivative, the factor of it is right there. So you could say, okay, I'm going to let u equal x squared plus 4, then du equals 2x dx, and then 1/2 du equals x dx. And life is good. X dx, and we are ready to go. Okay? But with a slight change, we have this integral now down here, where now we don't have this x, this factor of x up here, it's just dx. So u substitution is not going to work here. So we need something else. U substitution will not work here. So what we can try, I'm just going to do something here. I won't really explain it, but I'm just going to walk through this problem with a technique we're going to learn today, just so you can sort of get the feel for it. Okay, so it's we'll call it a substitution, but it's sort of like an inverse substitution. But this is what we're going to do. We're going to let x equal 2 tangent of theta. And again, after the problem's over, I'll explain exactly why we're doing this, but I just want you to get a feel for what we're doing. So we let x be 2 tangent theta, then dx is going to be 2 secant squared theta d theta. And then from here we're going to take this that we just came up with and substitute it in here. So dx right here, I'm going to write 2 secant squared theta d theta. And x here, I'm going to write 2 tangent theta. Okay, so when we substitute these in, we will get something like 2 secant squared theta d theta in the numerator. The denominator, we've got x squared. Well, x squared is going to be 4, right? Tangent squared theta plus 4. Right, because x squared, if I square x, I square this, I'm going to get 4 tangent squared theta. And then over here, we can notice that we can do something here. We could factor 4 out of here. So we could factor 4. I'm also going to do something else. I'm just going to leave this like this. I'm going to write d theta off to the side here. And I'm going to factor out this 4 to get tangent squared theta plus 1. Okay, and then of course what we could do here, we could take this 4 out of here, right? We could take the 4 out of here. Well, actually, let's just notice this. What's tangent squared theta plus 1? Well, tangent squared theta plus 1, that's a Pythagorean identity. Isn't that just secant squared? Right, tangent squared theta plus 1 is secant squared. All right, just a quick review here. We have sine squared theta plus cosine squared theta equals 1. And then we have tangent squared theta plus 1 equals secant squared theta. Now this just comes from starting here and dividing everything by cosine squared theta, right? Cosine squared theta, cosine squared theta, cosine squared theta. Now also if you divide everything by sine squared theta first, then you're going to get cotangent squared theta plus 1 equals cosecant squared theta. Okay, you don't see this one as much, but we're looking at this one right now. Tangent squared theta plus 1 is just secant squared theta. So I'm going to rewrite this as 2 secant squared theta d theta. And down here we're going to have 4 secant squared theta. All right, well, we can see that these are both perfect squares. I can take the square root of 4 and get 2, the square root of secant squared and get secant. So if we do that, we'll get 2 secant squared theta. And here we'll get 2 secant theta d theta. And we can see that the 2's will cancel. All right, those will cancel. And we'll basically just get secant theta d theta. Now this one we saw this one in section 7.2, right? We multiplied this by 1 in the form of secant theta plus tangent theta over secant theta plus tangent theta, and we came up with an answer for this. So the answer for that is just natural log secant theta plus tangent theta plus c. Right? So we know the answer to this. And now the last thing we just have to do is we have to look back to the original question. The original question was all x's, right? No thetas. So what we do is we're going to start here. We have to convert these theta, get rid of these thetas and put the x's back. So we're going to start here with this original substitution that said x equals 2 tangent theta. Okay, so I'm going to go back there. So x equals 2 tangent theta. So what that means is that tangent theta equals x over 2. And what we'll do every time with this trig substitution is draw a triangle based on that. Here's theta. Tangent of theta is x over 2, right? It's opposite over adjacent. And then by the Pythagorean theorem, we can find this side, right? Isn't this going to be the square root of this squared plus this squared? So that's just going to be the square root of x squared plus 4. And you notice that x squared plus 4 in this hypotenuse, that's this right here. So something about this substitution we did sort of builds this as part of this triangle. And then we can figure this out, right? So we can look at secant theta. Here's theta. Well, what's secant of theta? Well, myself, I don't ever use secant. I just use cosine. So I'm going to find cosine of theta and take the reciprocal. So cosine of theta is 2 over the square root of x squared plus 4, which means secant theta is the reciprocal of that, which is the square root of x squared plus 4 over 2. So we can say, all right, so the answer here is a natural log of the square root of x squared plus 4 over 2 plus tangent of theta. Tangent of theta is x over 2 plus c. And so this is the answer. And we did this with trig substitution, although I didn't really explain why we were doing it. I just wanted you to get a feel for it. Okay, so now let's look a little closer and see why this was chosen. So we've got this little table here, and this is just going to actually take a little bit of practice. I always write them in this order when I'm just trying to practice. When I was first learning, I'd start with a squared plus x squared, and then the next two are subtractions. So addition, it doesn't matter what order you go in. So of course there's just going to be one, but when you subtract, order does matter. So then I just kept the same format, a squared first, and then x squared. And then I just tried to remember it from this order, tangent, sine, and then finally secant. So when you use these substitutions, and we go through the process that we went through, then these parts that are under the square root will appear in the triangle, and it allows us to solve these. So when we see these integrands, we're trying to integrate, and these are part of the problem, we need to think of these substitutions. So notice that it's going to be x equals, and then the square root, right? So there's a squared, so we want it to be a, right? A squared a squared a. So when you look at this one, to determine the correct trig substitution, you get x squared plus 9. What's a plus? It's a plus, so it's going to be a tangent, right? Whenever there's a plus, there's a tangent. You can kind of even think of the plus looks like a t, right? When there's a plus, think of t for tangent. So looking at this one, the substitution here is going to be, what we would do is we'd say x equals 3 tangent theta. Right, I'm taking the square root of 9 to get 3. So x equals 3 tangent theta. That's this right here. Okay, so let's have you guys try the next two, B and C. Try B and C on your own. So press pause and see what you come up with, and then check back. Okay, so hopefully you guys are doing this right. You're not just waiting for me to tell you. Hopefully you're thinking about it already, and you tried it out. This is subtraction. The constant is first, right? Constant, then variable. So when the constant is first, that's a sign substitution, right? So what we're going to have to do here is just go x equals 5 sine theta. All right. Now this next one's a little trickier because it's 4x squared, but we do the same thing. It's a plus, so it's going to be a tangent. So the square root of this is 2x, right? So what we do here is we say 2x equals 3 tangent theta. So we just stick to this format and it'll always work. So the square root of this is 2x equals the square root of that times tangent theta. Okay, let me add one on here that's going to look sort of like b. Let's call this b and a half. What if we had x squared minus 25? Well, that's a variable first, right? Variable first, so it's going to be secant. So this is going to be x equals 5 secant theta. Okay, so these are similar, these two. But when the variable is first for the subtraction problem, it's going to be a secant. All right, so now we come up with one that's a little more challenging. It doesn't even look like it fits the format. But what we might have to do with one like this, when it doesn't really look like it fits at all, it is a second degree equation. So what we're going to have to do with this one is we're going to have to complete the square. Okay, some of you are probably thinking, I remember something that sounds like that. Something maybe from an algebra class. So that's what we're going to do. We're going to complete the square. So maybe a little rusty on this, but basically what we do is we're going to take what we've got here, but I'm going to put it in order from highest power to lowest power. Because we wanted to get in this ax squared plus bx plus c form. But then what we want is the lead coefficient to be a 1. It has to be a 1. So what I'm going to have to do is divide this 1 out, or divide this negative out, and write it like x squared plus 2x minus 3, right? So just to get rid of this, we want this lead coefficient here to be a 1. So I'm kind of just going to ignore this negative till we're done. And now when you complete the square, what you do is once you have a coefficient of 1 here in front of the x squared, you look at this, and this thing, you take half of it. So whatever that is, you take half. Right, so I take half of it, and it becomes a 1. And then whatever that thing is, you square it. So I square the 1, I still get a 1. Okay, then what I'm going to have to do is add that back in up here. Okay, got to add it back in. So I'm going to add this back in, but at the same time, I'm going to have to subtract it because I can't change this. Okay, so what will happen is I'm going to rewrite this. I'm going to write it negative x squared plus 2x. I'm going to leave some space there like this. Okay, because what we're doing is we're making this be a perfect square. And the negative 3 is not going to be part of it. So this 1 I put back here, so I go plus 1. But then to make me not change the problem, I have to go minus 1. Because now I'm not changing it, because plus 1 minus 1 means I didn't really change it. It's still this, right? But the key is now this is going to be a perfect square trinomial. So this we can factor into a product of perfect squares. And then this we'll just kind of put together. So looking at this, okay, I'm gonna try to make this more obvious by putting brackets. I'm gonna square and then put negative 4. Okay, now the negative 4 is just minus 3 minus 1. And now these are this being factored. So if we go x times x, 1 times 1, and plus, that works. And then this is just the same as negative x plus 1 squared minus 4. And just to make it easier to work with, I'm going to distribute the negative through, and that'd make it a positive 4 minus this. So if you distribute the negative through, we'll get 4 minus x plus 1 squared. Okay, so really what we've got, this original problem, is really just this, okay, under the radical. So let me write this. So this thing is really the same as 4 minus x plus 1 squared, right? Those are exactly the same. But with this format, we can see it's going to be a constant minus the variable. So if we just stick to what the box says up there, this is going to be x plus 1 equals 4 sine theta. So even when they don't quite look like that, by completing the square, we can put it in that format, right? This is the a, and this is the x, although it's x plus 1 this time. Okay, so there aren't too many like this, but this shows that this trig substitution is something that used to be used like in the bad old days before we had graphing calculators. And if you had some integral that you couldn't solve, you just had to try to find somebody who could solve it. There was no internet, no calculators or computers. So this trig substitution would sometimes work on these crazy integrals. Now nowadays we don't spend so much time on it because you don't need to. Nobody spends 45 minutes on an integral anymore because there's too many solutions out there. You can use an iPhone with an app on it. So there's certain things we just don't do anymore. Nobody does square roots by hand anymore. So integrals are we're doing them a little bit less. So we don't spend as much time on trying to integrate some seemingly impossible integral. Nobody does it anymore. But this technique used to be used more back then. So we'll still have to learn it, but we don't have to depend on it so much like we used to. But anyway, this sort of shows how to set these up. And once they're set up, everything falls into place. There's some trig. There's a decent amount of trig when you use this technique, as you can imagine. But for the most part, things fall into place fairly nicely once you get it set up. Okay, so let's take a look at one and see what we can do. First of all, just look at the format and just take a second and write down your substitution. Okay, don't wait for me. Press pause and see what you can come up with. All right, now hopefully you pressed pause and you're not cheating, because it's good to practice. We have to practice this. Notice it's a minus, right? And the constant is first. So if you look in the little box there, when the constant is first and it's a subtraction, that means you got a sign. It's going to be a sign substitution. So I need the square root of this. Square root of 9x squared is 3x. So when you go 3x equals, the square root of 1 is just 1, so it'll be 1 sine theta or just sine theta. Okay, so what I want to do first is solve this for x. Okay, so this means that x is equal to 1/3 sine theta. So once you do your substitution here, you want to solve it for x, okay? And then once you solve it for x, then you want to find dx, okay? So dx is going to be 1/3 cosine theta d theta. And then once you're here, then it's just we substitute. We just do a bunch of substituting. So here's dx right here. This dx, I'm going to put 1/3 cosine theta d theta. Okay, and I'm just going to put all these pieces in place. So x is equal to 1/3 sine theta. I've got 9x squared. So I'm just going to put 9 times this squared. And just see what we get. Okay, so this is going to be, get 1 minus 9 times x squared. Well, what's x squared? X squared is going to be 1/9 sine squared theta. Right, because if I square this, I get 1/3 times 1/3, which is 1/9 sine squared theta. Okay, that's under the radical. And then I have times dx, and dx is 1/3 cosine theta d theta. All right, so looking at this, I can distribute this, well, not distribute, but just multiply this, right? I'll multiply that, so we're going to get 1 minus sine squared theta. Now the 1/3, I guess we could bring out in front of the integral, right? Cosine theta d theta. And we'll get all these nice cancellations. Isn't 1 minus sine squared theta, isn't that just cosine squared theta? Right, so this is really just 1/3 cosine squared theta times cosine theta d theta. And then we've got the square root of cosine squared, which is just cosine, right? So this is really just 1/3 cosine theta times cosine theta d theta. Right, because you got the square root of cosine squared, that's cosine, times this cosine. So you've got 1/3 cosine squared, right? So really what we've got is 1/3 cosine squared theta d theta. Okay, I wonder if we ever learn how to do something like cosine squared. Well, hopefully everybody did their 7.2 homework, because if you did, then you'll know we got an even power of sine or cosine. We do those trig substitutions, right? We do that trig identity, actually. Trig identity we use for this. So remember we learned that we had sine squared theta and cosine squared theta, right? We said, well, cosine squared is 1 plus cosine 2 theta, but sine squared all over 2. Sine squared is 1 minus cosine 2 theta all over 2. That was from section 7.2. So we can do that right here. Now when I put the, well, let's just do it. Let's just do it this way. So I've got, this will be 1/3 times cosine, actually, let's see, 1 plus cosine 2 theta over 2 d theta. And then, of course, this 2 here I can pull out front. It's because it's really just 1/2 times 1 plus cosine 2 theta. So I'm going to pull that out front. And I have 1/3 times 1/2, which would be 1/6 times 1 plus cosine 2 theta d theta. Okay, and then from here, what we can do is we can integrate, right? We can start integrating. So this is going to give us 1/6. The antiderivative of 1 with respect to theta is theta. And then this will be plus 1/2 sine 2 theta plus c. Right, because I'm integrating this cosine 2 theta. So if this just said cosine of theta, I'd say sine of theta, but there's that 2 theta, right? So it's like a little mini u substitution, which after 7.1 and 7.2, you probably don't really need to do it like this anymore, but it'd be like when you said u equals 2 theta, du equals 2 d theta, 1/2 du equals d theta, and then you go through the substitution, and this factor of 1/2 is in there, so that's where we get the 1/2, right? Okay, so now we've got an answer in terms of theta, but we need our answer in terms of x. So what we can do is we go back here. So I'm going to go back to this 3x equals sine of theta. 3x equals sine of theta. Okay, so I'm going to draw, based on that, I'm going to draw a little triangle here. We'll draw it right here. So 3x equals sine of theta, which means sine of theta equals 3x over 1. So sine of theta is 3x over 1, right? Opposite over hypotenuse. Well, we can find this by the Pythagorean theorem, right? So if this squared plus this squared equals this squared, then this squared is going to be the square root of that squared minus that squared. Right, so this side is going to be 1 minus 9x squared under the radical. And then sure enough, 1 minus 9x squared is our integrand here. So we can use this to find theta. Okay, so if we go back again, and let me just write this down again. So 3x equals sine of theta. But let me write it a different way here. So I'm going to write sine of theta equals 3x. Because right here we need to find theta. Right? We need just plain old theta. Well, sine of theta is 3x, right? So theta, to find theta, don't have to take the inverse sine of each side of this. The inverse sine of sine of theta would just be theta, right? Inverse sine. So I take the inverse sine of each side, and I'm going to get theta equals the inverse sine of 3x. So that's what I put right here. Okay, so this is going to be equals 1/6. Well, actually, you know what? Before I even do that, let me talk about some other problem we're going to have, okay? We've got a problem right here. This will come up sometimes when we have an indefinite integral. If we have a definite integral, it won't matter because we're going to plug in endpoints. But here, this is talking about sine of 2 theta. I don't know anything about 2 theta. I only know theta. So if I have an angle of theta, I know how these sides act with theta. But if I double theta, can I just say I'm just going to double all these? No, you can't, right? If I change this from theta to 2 theta, these are going to change in a way that we don't know, right? So we can't use 2 theta. Okay, so we can't use 2 theta. So what we're going to use is an identity that we'll see a lot. Okay, I'm going to write this one down because we'll see it a lot. We're going to use this identity that says that, trying to make it so it's not so cluttered, but sine of 2 theta equals 2 sine theta cosine theta. Now this is an identity you've seen before, maybe not a lot, but we'll see it a decent amount in chapter 7. Sine of 2 theta equals 2 sine theta cosine theta. So this gets us from 2 theta to theta. That's what we need. We know all about theta. We know nothing about 2 theta. So we're going to have to rewrite this, okay? So I'm going to first rewrite it before I plug anything in. All right, 1/6 theta plus 1/2 sine of 2 theta, which means 1/2 times 2 sine theta cosine theta plus c. And of course, this is equal to 1/6 theta plus 1/2 times 2 is just 1, so I get sine theta cosine theta plus c. Now at this point, we are ready to go. We just got thetas, right? We figured out what theta is. We said that theta equals inverse sine of 3x. Okay, so we can finally put these pieces together. Make a little room here. These problems sometimes take some room. You're going to get your money's worth with this section because some of these problems take some room here. So 1/6 theta, theta is inverse sine of 3x. And then plus sine of theta, well, sine of theta is 3x. Cosine of theta, if we look over here, cosine of theta is adjacent over hypotenuse, so that's just going to be the square root of 1 minus 9x squared over 1. So that's just going to be the square root of 1 minus 9x squared. And then we have plus c. So what we should probably do here is distribute this 1/6 through, and then it will cancel here, right? I'll get 3x over 6, which is just x halves, right? 1/2 x. So let's distribute that through, and then we'll call it good. Okay, so we'll have 1/6 inverse sine, or arc sine if you prefer, plus, now this is going to be 1/2 x times 1 minus 9x squared plus c. The 1/2 x is because this 1/6 comes through here, so I have 1/6 times 3, which is just 1/2, right? And that is the answer. So some of these they take a little work because we first convert from x to theta, then we have to go back from theta to x using the triangle. But for the most part, like I said, they fall into place. You just have to, go through there's a little bit tedious and pay attention on little details, and you should be okay. All right, we've got another one here. You can see it's got the same look to it. You've got a radical here, and we've got a x squared minus 4. So looking at this one has the variable first. So our substitution here is going to be x equals 2 secant theta. All right, so then dx will be 2 secant theta tangent theta d theta. And then we can start plugging things in. All right, so we've got x squared minus 4. We've got x to the 4th down here. We've got a dx here. So let's take a look and see what we've got. So x squared is going to be 4 secant squared theta minus 4. And let's see, x to the 4th is going to be 16 secant to the 4th theta. We've got dx, which is times 2 secant theta tangent theta d theta. Okay, and we've got this up here. We can see, this sort of thing will happen all the time with this when we do trig substitution. We can factor a 4 out. All right, so we're going to factor that 4 out, and we get secant squared theta minus 1. Down here, we've still got 16 secant to the 4th theta. Over here, times 2 secant theta tangent theta d theta. You could be canceling things too. The secant will cancel here. We've got a 2 and a 16. I'm just going to take care of this, though, because secant squared theta minus 1 is tangent squared theta, right? Because of the one identity, tangent squared theta plus 1 equals secant squared theta. So secant squared theta minus 1, right? If I just subtract 1 from each side, I'll get tangent squared theta equals secant squared theta minus 1. So this is really tangent squared theta. So let me do it like this way just to save a little bit of time here. So that's going to be 4 tangent squared theta under that radical, right? So can we just go right to 2 tangent theta? So this whole thing here is just 2 tangent theta, right? So this will give us, in the numerator, 2 tangent theta. And then down here we've got 16 secant to the 4th theta. Then out here we've got times 2 secant theta tangent theta d theta. All right, so let's start canceling now. So looking at the numbers, we really got 2 times 2 is 4 over 16, which is really 1/4, right? So I'm going to pull out a 1/4 out in front of the radical. And then we've got secant, which will cancel with one of those. So secant will cancel, make that secant cubed. And we've got tangent times tangent, so we'll have a tangent squared. So we have in the numerator tangent squared theta. Denominator, we've got secant cubed theta. Secant cubed theta d theta. So when we've got something like this, kind of an unusual integral here, right? We've got tangents and secants. We probably want to do what we learned way back in like pre-calc or in a trig class when you're working with trig identities and you get some weird one. And the kind of like the go-to method, just change everything to sines and cosines and then see what you get. So I'm going to do that. So tangent squared is really sine squared over cosine squared. Okay, so I'm going to write it like this. I'm going to go 1/4. Tangent squared is sine squared theta over cosine squared theta. Right, that's tangent squared. And just think this is really like tangent squared. Like, okay, let me just do something just to make sure we're clear here. I could think of this as like tangent squared theta over 1 times 1 over secant cubed theta, right? You could think of it like that. Because when you multiply fractions straight across, you get tangent squared over secant cubed. So 1 over secant cubed, well, the reciprocal of secant is cosine, so that's just the same as times cosine cubed theta d theta. Right, so then we'll get, these will both cancel out, cosine squared, and leave us with just cosine to the first power. So this gives us 1/4 sine squared theta cosine theta d theta. Okay, so that's one that we could have seen back when we were doing u substitution, right? Once we get here, isn't this just a u substitution problem? So I could say I'm going to let u be sine theta, and then du is cosine theta d theta. All right, so if I just go, all right, so u equals sine of theta, du equals cosine theta d theta. So there's the du right there, cosine theta d theta. So then this would be 1/4 u squared du, right, which would be 1/4 times 1/3 u cubed plus c, which is really 1/12 u cubed plus c. Right, so now I've got u, I got to turn that into theta, and then turn theta back into x's, right? So we've got a lot going on here. But as everybody, hopefully everybody can see this. This is just a u substitution, right? This is something we could have seen in section 5.5 to get here. We got the 1/4 out front here. So this is u squared. It wasn't written very well, but that's u squared du. Use the power rule here, so it becomes 3, and then we divide by 3, so we get 1/4 times 1/3. So we're here. Okay, now we need to make some room here. Now we need to resubstitute because u is really sine theta. Okay, so what this really gives us is 1/12 sine cubed theta plus c. All right, so we're getting closer. And now we have to go back and draw our triangle. Okay, so if you look back at the very front of the problem, our first substitution was x equals 2 secant theta. That was our substitution. So that means that secant theta equals x over 2. Okay, so if secant theta equals x over 2, we can draw our triangle here. Here's theta. Now I'm not even going to think of secant. I'm going to think of cosine. Cosine theta is 2 over x. So cosine is 2 over x, right? Because I never really think of secant. I just use sine, cosine, and tangent. So secant is x over 2. Its reciprocal function cosine would be 2 over x. So from here, adjacent over hypotenuse, 2 over x. And then if we use the Pythagorean theorem, this side, we know this squared plus this squared equals this squared, which means this squared is going to be equal to the square root of this squared minus that squared. So this is going to end up being x squared minus 4 under the radical. Okay, so once we've got that, then we can finally finish our question. So sine cubed, so sine of theta is opposite over hypotenuse, right? So sine of theta is this over this, and we have to cube that. So what we end up getting for our answer is 1/12 x squared minus 4 over x, and we cubed that, plus c. And you can leave the answer just like that. All right, so we just take sine cubed theta. Here is theta. Sine of theta is opposite over hypotenuse. So we take that and cube it, and then add c, and that is our final answer. Okay, now I know what you're probably thinking is, that sure is good so far, but what about definite integrals and limits of integration? Well, let's take a look at that right now. So there's a little note here. When evaluating definite integrals using trig substitution, right, trigonometric, however you want to say it, trigonometric substitution, it's generally easier to change the limits of integration rather than using dummy limits. Now, most students I've noticed like to do that anyway. This means, like, once you change your limits of integration, then you never go back, right? You just change them and have a new problem. All right, so just to see how that works, let's try the definite integral, right? So this one, unlike the other ones, is a definite integral, so our answer is going to be a number, right? Before we were getting, our answer would be a function plus c, because they were indefinite integrals, but this is a definite integral, so we're just going to get a number for our answer. Okay, so looking at this one, we first just have to figure out which substitution we're going to use, and this is a variable squared first minus the constant squared, which is a secant problem. So this is going to be, our substitution will be x equals 1 secant theta, or x equals secant theta, which means that dx equals secant theta tangent theta d theta. Okay, now we did the substitution here, so once I start changing this, I'm going to do with these limits of integration too. Okay, so if we start going here, we've got x squared plus 1, so that's going to be secant squared theta, not plus 1, minus 1. Minus 1 under the radical, and then x down here is going to be secant theta, and dx is secant theta tangent theta d theta. But we've got these limits to worry about, so x goes from 1 to 2. Okay, so we have to go back up here and say, okay, well, go back to our original substitution, right up here. Go back here, we're going to say, okay, if x equals 1, then let's see what we would get. We would get secant theta equals 1, right? Now, I'm not going to use secant. I'm going to use cosine. If secant theta equals 1, that means that cosine theta equals 1 over 1, which is still 1. So cosine theta equals 1, what is theta? Okay, so to figure this out, something I didn't mention is that when you come up with these substitutions, behind the scenes, you need one-to-one functions. So to make them work, there's bounds on what these thetas can be. But it's actually easy. Just think about the most natural one when you think about the origin. Basically, you just think about between negative pi over 2 and pi over 2. You'll typically be okay on these. So cosine theta equals 1. What's the most obvious answer for the cosine graph? Right, so here's pi, 2 pi. Doesn't cosine just go like this? So cosine theta equals 1 right at 0, right? So you could say, okay, so theta equals 0. So again, I want to make sure you guys can see this. So think of, like, when you're doing this, when you just figure out cosine theta equals 1 and you're looking for theta, it's going to be the ones right around the origin. Just think of the most common, the first choice that comes to mind, and that's the one you're going to want to use. So theta equals 0. Okay, so I'm going to put a 0 over here. Now we also have x equals 2, right? This is x equals 2. So if we do the same thing, if x equals 2, that means secant theta equals 2, which means that cosine theta equals 1/2. Okay, so cosine theta equals 1/2. So if we think about where that would be, think about like either the unit circle or special triangles, but I'm just thinking, okay, cosine theta equals 1/2. Well, cosine theta equals 1/2, it's positive, cosine is positive in these quadrants here, right? Cosine theta is positive wherever x is positive. So if cosine theta equals 1/2, also, of course, to do this with our inverse cosine is defined in these quadrants, right? So between it being positive, which means these two, and where inverse cosine is defined, because aren't we going to really take the inverse cosine of each of these? So that means we're going to be in this first quadrant right here. So cosine theta equals 1/2. So if this is theta, cosine theta equals 1/2 means we got 1, we've got 2 here. So by Pythagorean theorem, this is going to be the square root of 3. So our cosine theta equals 1/2. That means this angle right here, that's going to be a 60-degree angle, or pi over 3, right? So if cosine theta equals 1/2, theta equals pi over 3. Okay, now this is stuff that sometimes we're a little rusty on. This is right triangle trig. Right, so solving these trig equations is something that you cover in pre-calculus and in trig class. So if you want a little refresher, if you're a little rusty, just look up solving trig equations, and you'll work with these kind of things. And you know, like I said, sometimes you can get a little rusty on them, but a little practice, things are much easier to learn the second time than they are the first time. But we're going to have to be able to solve these little trig equations. But again, the thing to keep in mind, they're always going to be kind of a simple answer, because the way these are defined. To make these things work, we needed to use functions that are one-to-one functions, and to make those restrictions, we're typically between negative pi over 2 and pi over 2. Okay, so our cosine theta equals 1. It's not going to be some answer way down the line here. Okay, just think of the most obvious choice, and you'll almost always be right. Okay, so back over here, we've changed these limits, and now we can do some canceling. We've got a secant theta, so we can definitely get rid of those. Also, we can see we've got a secant squared theta minus 1. Okay, so that's really a tangent squared theta. So we got 0 pi over 3. Under here, we've got tangent squared theta under the radical times tangent theta, d theta. Of course, tangent squared theta under the radical is just tangent theta. All right, so really what we've got here is 0 to pi over 3 tangent theta times tangent theta d theta. So this is going to give us 0 to pi over 3 of tangent squared theta d theta. All right, now this part, sometimes we can get a little bit hung up here. So the hint is, so we don't know of a trig function whose antiderivative is tangent squared, right? Think of the trig identity, the Pythagorean identity with tangent squared. Right, we've talked about this one a couple of times, right? So we know that tangent squared theta plus 1 is secant squared theta. So that means that tangent squared theta is secant squared theta minus 1. And it makes a really big difference if we do this, because all of a sudden you're going to see that we know the antiderivatives to both of these, right? The antiderivative to secant squared is just tangent. Antiderivative to 1 is theta. So once we have it like this, we can answer the question. This is just going to be tangent theta minus theta from pi over 3 to 0. And remember, we've changed the limits of integration, so we can just finish this problem. We don't have to go look back up here or anything. We can just plug these in. We change the limits of integration, so just like always, we just finish the problem. So you have tangent of pi over 3 minus pi over 3 minus tangent of 0 minus 0. Okay, well, first of all, tangent of 0, that's 0, right? Either think of the tangent function You think of the graph of the tangent function. So the tangent function is sine over cosine. Wherever cosine is 0, it's got a vertical asymptote. Tangent goes like that. Or you can just think, well, tangent is sine over cosine. Sine of 0 over cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. So that's 0. So this would give 0. So we basically have tangent of pi over 3 minus pi over 3. Well, pi over 3 is right here, right? This is pi over 3. So the tangent of that is opposite over adjacent. So square root of 3 over 1. So basically the answer to this question is the square root of 3 minus pi thirds. Kind of a weird looking answer, but the answer nonetheless. So that should get you started. These, they take a little practice, but you know, once you get started, you'll see that for the most part things fall into place. You get a lot of canceling. It's just going to be a really good review of trig. There's a lot of trig in this section. So give it a shot, and if you have questions, just let me know.